Okay, testing. So testing has already been part of the previous exercise, and it's part of this exercise. And the reason why we include it in the exercises is that it's extremely important when you do software development. So it's important because it prevents you from making mistakes, and it prevents you also. It also ensures that your code works in kind of the long-term future. So imagine if you write a script today, and if you don't write tests, right, and then a year later you start making adjustments to that script, and you fix it, you kind of generalize it to another domain, then you have no idea if the script still works on the original purpose that you've written. Right? So the idea with these tests is that you kind of have a bunch of test suites that you can run, that, and if they're all successful, then you know that your script still works as it was intended to. It's often also kind of almost a user guideline on how to use certain functionality of your program and what your program can do. And so even more, this becomes even more important if you have multiple people collaborating on the same program. Right? So it's very easy if you have five or more people working on one program, then someone else might break your functionality, and no one realizes if you don't have tests that cover that functionality. Okay, so let's see. So why should we test? So we want to check the correctness of the software. We want to make sure that future changes do not break functionality. And we also want to make sure that our software runs on a different environment. Right? So, for example, maybe Python is being upgraded, maybe the libraries change over time, or you run your script on a different operating system. So there are a few options that you have in Python when you want to write tests. So obviously you can just write your own test functions and run them. But there are some libraries that simplify your life when you write tests. And so in particular, there's Unitest, Doctest, and PyTest. Both of them are fairly common, but I will only show you how to use PyTest. So how do you use PyTest? Let's say we have a script that contains a function absolute value. We have an implementation here. So we want to check that this function works as intended, right? So what do we need to do? We create another file that is called test_script.py. So here the only important part really is that the name starts with test, so that PyTest knows that this is a script that should be executed when it runs the tests. But I call it test_script.py to infer that we're testing this script.py function. Okay, and so in here, what we do is, well, we obviously import the function that I want to have tested. So that's this line. And then I create a test function. And this test function now runs a bunch of experiments and makes certain assertions about what the result of that experiment should be. So for example, I say the absolute value of -3 should be equal to 3. Right? That makes sense. Another test would be the absolute value of 5 should be 5, and the absolute value of 0 should be 0. And so I use this assert statement here, so that's a Python keyword, to check the truth of that assertion. So if that condition here fails or evaluates to false, then the program will stop. It will erase an error, and PyTest will then will show you exactly where the error occurred and will help you in how to fix it. So when you write these tests, so this is kind of the principal format. When you write these tests, make sure that you have enough assert statements to cover kind of all the important cases. Right? So if you have an absolute function, you kind of have the case where the value can be negative, the value can be positive, or the value can be 0. Right? And these are kind of exactly the 3 cases that I checked here in these assert statements. So now we have 2 files in our directory, script.py and test_script.py. And so now I can actually run the test suite. I can run pytotest. And the way I do that is I do it in the command line. So you call py.test and then the test file, test_script.py. And then -v just means I want to have additional output. So it means it's the verbose flag. So I run this, and then I get some output. So you see it tells me a little bit of background information, which Python version am I using, and so on. So this is quite useful if something goes wrong. And then it shows me here, it executed in test_script.py, it run this function testfunc. So that's exactly the one up here, right? And then it tells me it failed. So something is going wrong. And now down here it tells me exactly, it tries to help me a little bit on what's going on. And so we can see it's this assertment that failed, right? And so I was testing absolute value -3 should have been 3, but when it evaluated it, it turned out to be assert -3 equals 3. So clearly, absolute value of -3 evaluated to -3 instead of +3, right? So this indicates that actually my implementation of absolute value must have been wrong. So now if you look here, right, so what I did is if x is smaller than 0, then I returned x rather than -x. Right, so I made a mistake here. The minus and the plus should be swapped here. So that means we can fix our implementation. Anyways, let's not do that now. But assuming that I fixed now the implementation and I would run it again, fine, let's do it. So we're in here. So there's the script.py. And so the mistake was here that I had a minus, right? And I needed to swap it. So now the implementation is correct. So now I can go back here and can write py.test test script -v. I can run it, and now it tells me the test passed. Okay? So it's should be hopefully fairly straightforward. So good testing practices. So this should be fairly obvious, but it's also very easy to just neglect it. So when you develop new features, make sure that you add new tests at the same time. Furthermore, make each test kind of a unique and standing alone example. So you shouldn't be too complicated. Ideally, you should test one functionality, and each test should test exactly one functionality. So that will make it much easier. If something breaks, you know exactly where you need to look when it breaks. Tests should run quickly, so don't make your tests download gigabytes of data or run computations for an hour, because you want to execute tests all the time. So ideally, whenever you change something, just run the test for 10 seconds to make sure that everything is still working. So in a professional software environment, you will actually see that on GitHub, for example, you can set it up in such a way that whenever you push changes to GitHub, it will run the test suite automatically on remotely on GitHub or on another server. And it will only, in fact, sometimes it will only allow you to kind of push the changes when all the tests pass. Right? So you can be quite strict about that. So when you choose names, like whenever you do programming, make sure that you give descriptive names so that it's easier to figure out what's going on. And just a general hint, so sometimes people are not so good at documenting their code, but it's often quite useful actually to look at how, because tests are in some way, tests are just kind of use cases on how to use the code. So it might be sometimes smart to just look at, if you look at a new code, you can just look at through the test suite and see how that library is being used, for example. Okay? Good. That's all I wanted to say about testing. Okay. The next part is numerical Python. So far, we've covered mostly kind of basic Python. Today is the first time that I'm talking about a extension, a specific library, Python library. It's called Numpy for Numerical Python. And it's probably one of the mostly used Python library. So most extensions or most libraries that you might use or download or write yourself will probably use Numpy in one way or the other. So for that reason, it's really important to know what it is. So I will, today we'll talk about basically all the core Numpy functionalities. So I will show you how you, first kind of a quick introduction, then I will tell you how you create arrays, then you learn how we can index arrays, how we can random numbers, you learn about structured arrays, you learn about how to write high-performant code using Numpy. You learn a little bit about linear algebra and how to plot data. So if you want to know more about it, there's a lot of information online. So there's just some links up here, and yeah, I've often referred to them if I want to know something more specific about a function. So here's here's kind of how we load up Numpy. So we can just write import Numpy, and it's quite common that you create an alias. So often that alias is called just NP. That saves you quite a lot of typing when you use a lot of Numpy functions. Then you can just write NP dot rather than Numpy dot. And so when do you want to use that module? Well, typically whenever you want to do efficient numerical computing, right? If you want to do kind of data analysis or some maths on a bigger scale, then Numpy is the right answer. And so the reason why it's so efficient is because it stores arrays continuously. Right? So it allocates a bunch of memory, and that's where it stores the data that you're computing with. So that's in contrast to lists. So lists are kind of, there's no promise on how the data is stored. So lists are typically quite inefficient compared to Numpy arrays. Numpy is written in C and Fortran. That's another reason why it's so fast. So essentially, whenever you call Numpy functions, you're calling straight out to C or to Fortran function, and then the actual heavy computations is being performed on the C level or the Fortran level, right? So Python really often now, Python is really just the highest level, and all the heavy duty happens on a C implementation or Fortran implementation. But you don't see it as a user, it's just good to be aware of it. And so Numpy is basically today the quasi-standard. So there has been previous alternatives, like Numeric from the mid-90s, Numarray from about 2000, and then from 2006 there was Numpy, and since then it has kind of dominated the numerical Python libraries. So here's a first example. So we will dissect it in a second. I just want to give you the full program. So this is roughly maybe 20 lines of code or so. And what it does is it fits a line through a set of XY data points. Right? So imagine you have some data points and you want to find kind of the offset and the steepness of a line that fits as best as possible through these data points. So that's the associated code with it. And then this is how an output could look like. So you kind of, these blue dots, these are the data points that we have. they stem from a original to line, so there's kind of a to data line that we have, and we taught samples from that line and added some noise, right? So essentially, the way you get these blue points is you take a point on that red line and then add some noise. And so we did that 50 times or so, then we obtained these 50 data points. And then we did this best fit using least squares, and then you get this blue line, right? And so the blue line is the reconstructed line purely from the data points. And so you can see that they are almost the same. Yeah, so 20 lines of code for quite a complex operations. And we'll go through it bit by bit now. So let's see. The first line is simple. So in the first line, we just import Numpy and create an alias np so that it's a bit more convenient later on. The next line, what we do is we create data points. And so the first 3 lines create the data points on the x coordinates where we want to get data points from. So n is just the number of data points that we want, and then np.linspace. So this is now our first Numpy functions that we're using. So basically it says is we want n data points in the range from 0.0 between 0.0 and 1.0. Right? And so then we can print that, and here's an array of all the points where we want to evaluate. So then we want to also generate the associated y values, and the way we do that is we compute them using the exact line, so the exact function that we have. So we just, our true relationship between x and y is -2 times x plus 3, right? And so we evaluate the truth, and then we add some noise to it. So this is what the next line does down here. So we add normal noise with mean value 0 and standard deviation 0.225. And again, we need n random values for that. And then we just add that to the true values. And then the result will be another array that is exactly the same length as the x coordinates, that now contains the y coordinates plus some noise. So this was kind of the data generation. So now comes the linear algebra. So now we need to solve a least squares problem, and least squares, that basically, yeah.
What is noise?
So noise is just random. So basically what we do is we evaluate that function at every x point and just add a random number to it, right? So what we're trying to simulate here is that when you make measurements from the real world, right, you typically have an underlying model, right, like a physical relationship, right? But then you always make measurement errors, right? And these measurement errors, you can model them as kind of being random, right? And that's what's going on here. So we just say that, so this is kind of our true relationship. And then here's the mistakes that we're making. And these mistakes might be, yeah, it might come through various different ways. But essentially, we're losing information here, right? Our reconstruction can't be perfect anymore because now we've added noise to our data. Or, yeah, errors to our data. So now the next step is solving a least squares problem. And we don't need to understand this in detail, but essentially what it does, it tries to reconstruct the steepness of the line and the offset of our line purely based on the data, right? So we create some kind of an array here, and then we call the np_linear_least squares function on it. And so the only inputs that we provide is the x data and the y data, right? So these were the data points that we've created, including the noise. And then this, so this is an NP, this is a Numpy function that Numpy provides. And then we can extract AB. So if you do that, so then A contains the steepness or the gradient of the reconstructed line, and B contains the offset of the line at x equals 0. So in other words, kind of our approximated line that was obtained purely from the data is now y equals ax plus b. Okay, and so now we can plot it. So what we do for plotting, we use another module called Matplotlib. And so in particular, we use matplotlib.pyplot. And then you can write things like plt.plot. You provide some x points. You provide some y points. You can specify how it's being visualized, and then you get these nice plots here. And then you can do the same thing for our fitted line. So here I use this ax plus b with the a and b. These are the two functions that we reconstructed. And then finally, we can do the same thing with the original data. Okay, so this was kind of really a crash course on what Numpy can do, including data generation, some linear algebra, and then finally plotting the results. But okay, so let's a step back. Let's take a step back and start from the basics again. So the most basic type that we have in Numpy are arrays. And in some particular one, the typical arrays that you work with are called ND arrays. And these are n-dimensional homogeneous collections of items of the same type. So what that means is n-dimension just means that they can be one-dimensional or they can be two-dimensional. So these would be matrices or vectors. But you could also think about three-dimensional arrays, right? Or four-dimensional, or maybe 100-dimensional. So you're not constrained in the dimension. Homogeneous, so we have homogeneous collections of the same type. So that means they're almost like lists, but they have to have the same type. So here are two examples on how you can create these arrays. So use np array, and then you can pass in a Python list. And so essentially, it converts that Python list into a Numpy array. And you can do that with floating point numbers here, but you can also do that with strings. So the important things to remember, and that are different to when we talk about lists, Python lists, is that Numpy arrays have always this a fixed size. So once you've created a Numpy array, you can't change its size anymore. Right? So that's different to lists. In lists, we could append items and so on. With Numpy arrays, you have to decide once, and then you're fixed. Arrays have also just one associated data type. Right? So again, in lists, you could kind of mix integers and strings and so on. In Numpy arrays, you can't do that. You can only have the same types in the array. Which means, yeah. So there are different ways on how you can create Numpy arrays. I've showed you one here before, where you just provide a list. You convert a list into a Numpy array. Sometimes you might not have a list, or maybe you want to create a Numpy array that just contains of zeros. Then you can use np.zeros, and then you provide how many elements you want to have at the Numpy array. So in this case, we would get an array with 5 entries, and that would all contain zeros. There's also an associated Numpy function called np.once. So not surprisingly, you get a Numpy array with the number 1 inside. And then finally, that's actually, there's a function called np.empty. So that creates an uninitialized array. So when you do that, you don't know what the values will be. Right? So here they're just 0, but maybe if I run it again, there might be different values in it. So the reason why we have that is because NP-empty can be a little bit faster than NP-ones or NP-zeros, for example. Because you don't need to overwrite the memory and set it to 0. So this can be useful if you actually don't care what the value is in. You just want to allocate the memory for now and set the values maybe later on. Then it's often useful to create arrays that contain kind of numbers, that contain a sequence of numbers that are linearly spaced from a starting point to an endpoint. And if you want to do that, you can use Linspace. So Linspace takes 3 arguments, A being the starting point of the value range, B the end point of the value range, and then N the number of points that you want to have. And then it generates N uniformly spaced coordinates, starting with A and ending with B. So if you look at this example here, we go from -3 to 2. We have 5 points, and then the end point should be contained. So then we get -3, and then 3 more values, and then 2 is the last value. Right? So this endpoint equals 2 just means that you want to include that last number here, the second argument. If you set endpoint equals false, you get the same thing, but now you exclude that last number. So 2 would not be contained in that. So just remember so that often you might want to choose endpoint true or false explicitly depending on your use case. Then we have A-range. So that A-range works very similar to the Python's range. So in A-range is different in that you provide the start point and the end point and the step size that you want to have between each numbers. Right? So rather specifying the number of elements, you specify the number of coordinates, you specify the step size and the coordinates. So here in this example, I go from -5 to 6, and the step size is 2. I get this array out. And so obviously here my endpoint is 6, but here the final number is 5, and that's simply because if you try to go 5 plus 6 is 7, right, and then you would exceed the endpoint. So that's why 5 is the last element here. So there's a warning for A-range. So sometimes A-range can give unexpected results. And so in particular, the upper limit may or sometimes may not be included. So look at this example here. We're asking for a range of data points starting from 8.2, going to 8.2 plus 0.05. And the step size should be 0.05, right? So in a way, this looks logical, right? What we get out is 8.2 and 8.25, right? So this is exactly kind of the start point and the end point. But now I'll do the same thing, but now instead of using 0.05, I now go up 0.1. But for some strange reason now, I still only get 2 elements here. I don't get the 8.3, which you might think should be included. So that's in a way a bit surprising. And has anyone got an idea what's going on? Yeah? Okay, and why is that? Yeah. Well, it is. So you can see so it's unintuitive, right? In the first example, it's inclusive. In the second example, it's exclusive for some reason. And yeah.
Is it round of errors?
Yeah. So it's round of errors. So that's something that you. If something is surprising when you talk about numerical computations, the answer round of errors is almost always true. Right? It messes constantly with us. And so you see that very clearly. So in the first case, in Python, if you just write 8.2 plus 0.05, right, you're getting expected answer 8.25. But if you do 8.2 plus 0.1, you actually get 8.299999999. Okay, so that's what's going on. And so obviously 8.29999 is so kind of that's our end point here, right? And that's smaller than 8.3, and therefore it's not included. So just be aware when we talk about numerical Python, we suddenly hit, we work with floating point errors, and they have round-off errors. Okay, array attributes. So you probably can't read that. So, but when you have a Numpy array, you have a bunch of attributes that you can access. And so you might not always use them, or not always, but it's still always useful to know about them. So for example, so Numpy array has kind of an underlying data structure that you can access. And you typically don't want that, but if you wanted to access that, you could ask for a.data. Right? So then you would really get kind of the underlying buffer to the raw data that the array is storing. A.dtype is something that's really useful. That tells you the type of the items in that array. Remember, arrays always have only one type, and you can ask for its type by doing array.dtype. A.endim tells you the number of dimensions. A.shape, A.size tells you how many elements there are in that array, and so on. So this is sometimes quite useful. So let's look at one important example. It's this dtype. So dtype is the type of the element, about the elements in the array. And you can actually explicitly specify which dtype you want. So normally, Numpy tries to do it in a smart way, but if you want to specify it, you can say np0s, so 3 elements, and then the dtype should be integers. So then you get an integer array. You can say float 32 if you want to have floating point values, single position, or you can create an array with complex numbers. So here's an example how you can use these array attributes. So let's say you have an array and you want to create a new array that has exactly the same dtype and the same shape. And the shape just means if it's a vector or a matrix, and how big is that vector or the matrix, right? So the way you do that is you do np.zeros, then you pass in the shape of the original array, and then its dtype. And so essentially you get a copy of that array but zeros inside instead of the actual values. Oops. And so if you don't specify a dtype, Numpy tries to be smart and tries to pick a dtype that can contain all the elements that you passed in. So here, let's say you create an array and you pass in a list, and that list contains a floating point value, an integer, and a string. Now, Numpy will select a data type that can store all 3 of them, at least in some way. And the way it does it, it stores them as strings. So be aware that here implicitly a string conversion is going on. Right? And you can see here now 3.5 is stored as a string rather than a float. And so now we can ask for its dtype. So we can write a.dtype, and we'll see the dtype is this smaller u32, which essentially represents Unicode strings with maximum 32 characters. Right? So that's how Numpy decided to convert that array. Okay, then there's a bunch of more ways on how you can construct Python Numpy arrays. that one we've already seen. So if you list, you can just do numpy.array and then pass in that list. And as I mentioned already, the dtype is determined automatically. It also goes the other way around. So if you have a numpy array, it might be sometimes useful to get a list out of it, a standard Python list. And the way you do that is you write a.toList, right? And then what you get out is a list. But be aware that this is now a copy, right? So a list is now a standard Python list. It's a copy. One thing that's really useful is a function that can convert anything to a numpy array. And with anything, I mean integers, lists, tuples, arrays. So, and then it tries to convert it as a numpy array. And so the associated function is called np.sArray, and it converts that object into a numpy array. And if necessary, it copies it, but it tries to avoid copying. So if you call np.sArray and you pass in a numpy array, then it will not create a copy of the underlying data. But if you pass in a list, then it will create a copy. So the reason why this is useful is when you create functions with flexible arguments. So you want to create a function that kind of can take in a variable, but then inside that function you want to work with that variable as a numpy array. And so what you do is you take that argument and you pass it through sArray, and then A becomes a numpy array, and you can do operations on it as you want. And so now, with that trick here, you can use my function on lists, you can run it on tuples, or it also works on numpy arrays and even floats and integers. Does that make sense? Maybe? Then sometimes it's useful to initialize an array from a Python function. So let's say you have a Python function that takes in the x and the y coordinate, and you would like to create an array that contains this function evaluated at all these different coordinates, at a bunch of different coordinates. The way you do that is you write np.fromFunction, then you provide the function name, and then you provide the coordinates where you want to have it evaluated. So here going from 0 to 3 and 0 to 5 in the y coordinate. And then what you get out is an array of size 3 rows and 6 columns, and evaluated at all these different I and j indices. Okay? So then we have higher dimensional arrays. So I've been mostly talking about just vectors, but as I mentioned, Numpy can actually do arbitrary dimensional arrays. And the way you construct them is by passing in not just a single number in the constructor. So in NP0s, we normally just passed in a number, and that would specify the length of that vector. But now, if you pass in a tuple, then we specify, so the length of the tuple specifies the total dimension that we have, and the number in each tuple specifies how many elements we want to have in that dimension, or how many coordinates. So in this case, we would get a 3-dimensional array. In the first dimension, we will have 2 components. In the second direction, we will have 3 components. And in the third dimension, we will again have 3 components. Right, so that's a 3-dimensional array. And the way it's printed here is you have, so each innerst row here is 1. This comes from the latest dimension here. This is the 3. So we have 3 guys here. This is a 3 times 3, essentially this is a 3 times 3 matrix here, right? These are these 2 dimensions here. And then we have 2 components of these. So that's why we have 2 3 by 3 matrices. So that's what's going on. And they're all filled with zeros in this case. You can also create a two-dimensional array from two one-dimensional Python lists. So let's say you have an x vector and a y vector, and then you can pass in both the x and the y vector here. And what you will get is you will now get a matrix with the first vector as the first row and the second vector as the second row. So in maximum, you can work in 32 dimensions. And you can always ask for the shape of that object using a.shape. So for example, let's say, if you look at this case here, and I say np0s, so let's do a equals, and then a.shape, right? You get exactly the structure that you passed in here as an output again for a.shape. So if you're uncertain, you want to test if maybe you have a function that takes in a Numpy array and you want to check if it's a vector or matrix or third-dimensional array, and you want to check its size, then you can evaluate this a.shape attribute here. So one really useful thing is that you can actually change the dimension of an array, or you can change the shape of an array. And you can do that without actually copying the data. And the way you do that is you can also just write to the shape attribute. So let's say you have you create a Numpy array that just contains of a long vector, but now you want to view that vector as if it was a matrix. So what you do is you just reassign the a.shape attribute, and you say, okay, it now should be considered to be a 2 times 3 matrix. And then if you print the result out, you get the first 3 items of the original vector as the first row of that matrix, and then the next 3 items of that vector as the second row of the matrix. So of course, the shape here, if you multiply 2 times 3, that needs to be exactly the length of the original vector. Right? Otherwise, it would be not consistent. But as long as you can ensure that you can arbitrarily change, you can make a vector into a matrix or a 3-dimensional tensor, or so you can play around with the array dimensions as you want. And so the reason why that's possible is because Numpy stores the raw data just as a long consequent in memory. So it's just one block of memory with all the data in. And then the shape is just an interpretation of that data. Right? And you can have multiple interpretations of the same data. You can consider it as one long array, but you can also view it as a matrix with the first row stored first, and then the second row afterwards, and so on. So here the important part is that this reshaped array points to the same data vector. So there was no data copying going on. So to demonstrate that, let's take this. So now after these 3 lines up here, we now have a matrix. So I can now take the top left corner of that matrix and change its value to -10. And then I can reshape that matrix again to be just a single vector. So that's what I'm doing here. So now it becomes a vector of length, the full number of elements that I have in that matrix, and then the second dimension is just 0. So in other words, I'm just converting it back into a vector. And then if I print that out, I now have the original vector back, but the first element has been changed to -10. Right? So the raw data is always the same. It's just the interpretation that differs.
Excuse me.
Yeah.
If you try to do the A00 before you say the shape is supposed to be a matrix, would it still work? Or do you
No.
have to
yeah, so it doesn't. So here what you're trying to ask for is you're trying to get the element, the first element in the first dimension and the first element in the second dimension. But if you're talking about a vector, then there is no second dimension. So we can try it, but I'm pretty certain. I'm pretty certain it will fail. So you're trying to, so A0, right? A0 is just the first element, so A0 will be 0.0. And then you're trying to access the first component of a number, which really doesn't make sense. Yeah?
What if you try to sort of shape something, like say you have 7 points and you try to do the shape of 2 times 3 matrix? Would it
Yeah, so that is an interesting point. So let's say let's say I remove the 8 here, right? So now I just have seven numbers. So now I can't really convert these 7 numbers into a 2 times 3 matrix anymore, right? I have one component missing. So let's see what happens. Okay, it says it gives me a value error. Total size of new array must be unchanged, right? So you're trying to, the matrix expects kind of 6 elements. So you're trying to change a 5 element long vector into a 6 element long vector, and then Python complains. And so you need to make sure that you stay consistent in the total size of elements in your array. Okay, I think you deserve a break. So let's start again in 15 minutes.